Hello again. This week we'll be devoting our attention really to one word, and that word is the word dimension. Now, what we're going to do in this unit is we're going to think about what this word means. We're going to apply it to familiar geometric objects that you've known about for a long time, and then we'll turn our attention to fractals. And when we start looking at fractals and their dimensions, we're going to see something that might be pretty surprising. Let me say that there's no material in the textbook about this week's unit. What there is a set of notes called Notes on the Theory of Dimensions. Make sure that you look for these notes. Make sure that you read them. These recorded lectures are rather telegraphic. They're only supposed to give you a rough idea what's in there, so please do make sure you go find these notes and read them. So let's begin with perhaps the first idea about dimension. A dimension is a degree of freedom. So if you're talking about how many dimensions something has, you're talking about the number of degrees of freedom of motion, how many different directions you can move on that object. So consider a cube, and when I say a cube, I want to think about something that's solid. Okay, not just the faces of this as made out of paper, but perhaps it's made out of wood or something like that. And we all know that a cube is three-dimensional. That is to say, if we're moving within a cube, we can move up or down, that's one direction, or we can move backward and forward, which is a second direction, or we can move left and right, that's a third direction. It takes a triple of numbers, that is to say, a value of x and a value of y and a value of z to specify a location. Now let's look at the surface of a donut, which is called a torus. And I want to make sure that you're thinking just about the surface. So don't imagine all the lovely dough inside, but just the crust that's been in the grease and that has hardened up to make this crunchy, delicious crust. We're just moving on that crust. And if you can imagine that it's infinitesimally thin, really, then you've got the right idea. Now, I'm claiming that the surface of a donut is two-dimensional. So if we're standing at a point on this donut, imagine ourselves as a little insect or something crawling around on this surface. There's two independent directions we can move. Let me call your attention to a particular point, namely where that purple circle and the red circle are meeting. There are two circles going around the torus, and there's one point where they meet. Now, if you were standing there, there are really two independent directions you can move. You could move in the purple direction, or you could move in the red direction. Of course, you could move in both simultaneously, so you could go off on somewhat of a diagonal. But that's really not a new direction. That's just a combination of the other two. And you can also see that this is two-dimensional by seeing that everywhere you look, you're seeing what looks like a two-dimensional grid, just like on graph paper. So globally, it's wrapped up, but locally, it looks just like a piece of graph paper. And locally, it takes a pair of numbers, that is to say, an x and a y, to specify a location. The same thing can be said about the surface of the Earth. Again, it's two-dimensional. That is to say, if we're on the Earth and we're not allowing ourselves to fly up in a balloon or to go down in a well or something like that, we can only move in two independent directions, and it takes a pair of numbers to specify where we're located. And that's, of course, a quite familiar concept. On the Earth, we tend to use measurements which are called latitude and longitude. Notice a pair of numbers to specify a location. Another way to understand how one-dimensional objects and two-dimensional objects look is to think of them really zoomed way in. So over on the right at the top, I'm showing you an algebraic curve, and I claim that this is one-dimensional. And what I'm saying is, if I concentrate my attention at a point on that red curve, and I look very locally, I zoom way in, the more and more that I zoom in, the more and more that it looks like a line. In fact, one of the basic things that one learns if one takes a course in calculus is to figure out just what is the line that seems to be appearing as you zoom in. There's a name for it. It's called the tangent line. And in this picture, I'm showing you the tangent line to the red curve at a selected point on that curve. It's just the line that's going the same direction as the curve. If you would zoom in and in and in on that point on the curve, eventually it would look like that red curve was looking more and more like the line. Coming back to the Earth, the same sort of thing. If you look at the Earth from space, even quite a ways out, way off in the distance you can see that it's curved, but locally, right down below you, it looks like a piece of a plane. In fact, it took a long time for mankind to realize that we were not sitting on a plane. In fact, we're sitting on this sphere, the Earth. But still, locally, as we look around, it seems to be that we're on a planar surface. We're on a surface. Now, some objects that are familiar have pieces of various dimensions. So let me come back to that wooden cube. So that solid wooden cube is three-dimensional. We're free to move in three different directions. But we can look at pieces or aspects of that cube that are more restricted in how many dimensions they have. So for example, there are 6 faces. If you look carefully and think about it, you'll see there's a top face, a bottom face, a right face, a left face, a front face, and a back face. There are 6 two-dimensional faces. If you're only allowing yourself to move on the face, then you can only move in 2 different directions. So faces are two-dimensional. But we can restrict ourselves even more. We could say we can only move on the edges there. Imagine that maybe there's a wire frame, and we're only allowed to move on that wire frame. Well, there's 12 different edges there, 12 different pieces of wire, but moving on each one, we can only move in a single direction. So each of those edges is one-dimensional. And then finally, we could say we have to stand at a corner. Well, if you're standing at a corner, and you're not allowed to move away from it, then you have no degree of freedom of motion at all. And so the corners are said to be zero-dimensional. So it has 8 zero-dimensional corners. So let's recap. What we've said in this lecture is that the first notion of number of dimensions is the number of degrees of independent motion. And note that with this idea, if we take an object and ask what is its number of dimensions, then our answer always has to be a whole number, right? It's saying count, okay? So how many? It's the answer to a how many question. So it could be 0, it could be 1 or 2, but it can't be 1.5, and it can't be 2.12.